Have you ever wondered what secrets lie beneath crushing depths and blinding cold? On Earth, over 90% of our oceans remain unexplored, yet we've already discovered microbes thriving at a staggering 121 degrees Celsius and under pressures exceeding 1,100 atmospheres near hydrothermal vents. If life can flourish in those furnace-like conditions, could similar organisms exist in the hidden seas of Europa, where a subsurface ocean might hold twice the volume of all Earth's oceans combined? Europa's icy shell, battered by intense radiation, about 540 rem per day, conceals an ocean insulated by 15 to 25 kilometers of ice. Deep-sea microbes on Earth survive without sunlight by metabolizing hydrogen and sulfur compounds. On Europa, tidal forces generated by Jupiter's gravity could produce comparable chemical gradients. Imagine tiny life forms eking out an existence in a frigid, pressurized ocean, much like their counterparts in Earth's abyss. Could the discovery of one remarkable microbe on our planet be the roadmap to finding life on a distant moon? Picture Earth's deep ocean, a world of perpetual darkness and crushing pressure. In 2019, explorers lowered a probe into a hydrothermal vent field 3,400 meters beneath the sea's surface. Water temperatures there spiked to 121 degrees Celsius and pressures topped 1,100 atmospheres. Despite these extremes, a microbe named Thermodesulfobacterium geothermicum was living its best life, feeding on sulfur and hydrogen instead of sunlight. Meanwhile, about 628 million kilometers away, Europa, the smallest of Jupiter's 4 Galilean moons, hides a global ocean beneath a shell of ice that's 15 to 25 kilometers thick. Radar and magnetometer data from NASA's Galileo mission tell us that this ocean could contain up to twice the volume of all Earth's oceans combined. Europa's hidden sea isn't warmed by sunlight, it's heated from within. Jupiter's immense gravity stretches and squeezes Europa as it orbits, generating tidal friction that heats the moon's core. This heat likely powers hydrothermal vents on Europa's ocean floor, akin to those on Earth. If so, those vents could spew hydrogen, sulfates, and other chemicals into the water, creating the redox gradients that earthly microbes like Thermodesulfobacterium geothermicum exploit for food. Laboratory experiments back on Earth show that some deep-sea microbes can remain viable for weeks under pressures of 800 to 1,200 atmospheres and temperatures near freezing. So, if Thermodesulfobacterium geothermicum can handle a 100 degrees Celsius temperature range at 1,200 atmospheres, could Europa's hidden ocean, cold near its icy roof but potentially warmer around vents, offer a similar refuge for life? As we gear up to probe Europa's secrets, this microbe challenges our ideas of where life can exist. Next, let's dive into how researchers brought these extreme conditions into the lab. In July 2019, aboard the Ocean Explorer 2, scientists targeted a hydrothermal vent field at 3,400 meters depth, 250 kilometers off Papua New Guinea. Temperatures there soared to 121 degrees Celsius and pressures exceeded 1,100 atmospheres. From this hostile environment, they isolated a microbe dubbed Thermodesulfobacterium geothermicum. Genomic sequencing, published in February 2020 in Nature Microbiology, revealed that T. geothermicum uses reverse dissimilatory sulfite reductase enzymes to reduce sulfate into hydrogen sulfide, harvesting energy without sunlight. Most astonishingly, its proteins remain stable under a 100 degrees Celsius temperature span at pressures around 1,200 atmospheres, traits unheard of in other extremophiles. Under 1,200 atmospheres, equivalent to approximately 12 kilometers of water and fluctuating between 1 degree Celsius and 121 degrees Celsius. T. geothermicum maintains membrane integrity thanks to specialized ether-linked lipids that don't stiffen or melt. Why it matters? Europa's subsurface ocean is estimated to sit under 15 to 25 kilometers of ice plus approximately 100 kilometers of water, with pressures approximating 500 to 1,000 atmospheres. If a microbe can handle 1,200 atmospheres on Earth, it suggests even higher pressure tolerance might evolve elsewhere. Between June 2020 and December 2021, the University of Southampton's Astrobiology Centre cultivated T. geothermicum in hyperbaric bioreactors to mimic Europa's ocean. Pressure was sustained at approximately 800 atmospheres, simulating an 80-kilometre water column. Temperature gradients ranged from -1 degree Celsius to simulate regions near the icy shell, up to 20 degrees Celsius to simulate potential vent effluent. Salinity was maintained at 50 grams per litre of magnesium sulfate, reflecting Galileo data suggesting a magnesium sulfate-rich brine. A continuous supply of hydrogen and sulfate ions recreated hydrothermal vent chemistry. Over 6 months, researchers monitored cell division rates, metabolite production, and membrane stability. At -1 degree Celsius and 800 atmospheres, T. geothermicum exhibited 0.1% weekly population growth, slow but persistent. At 15 degrees Celsius and 800 atmospheres, growth increased to 1% per day. Metabolomic profiling in August 2021 detected methane and ethane byproducts, indicating active hydrogenotrophic methanogenesis pathways alongside sulfate reduction. Electron microscopy revealed flagella-driven motility under 800 atmospheres and -1 degree Celsius, proof that these microbes could navigate Europan currents near vents. Key fact: SWIDID analysis uncovered branched C30 isoprenoids that remain fluid at -1 degree Celsius and resist collapse at 20 degrees Celsius under high pressure. Possible biomarkers for future missions. Why it matters. If analogous lipids existed on Europa, a lander or melt probe sampling ice or plume ejector could detect them via mass spectrometry. Europa's interior heating stems from gravitational flexing. Jupiter's pull creates tidal bulges, generating frictional heat. Geophysical models from Caltech in 2022 predict localized hotspots where the ice crust thins near chaotic terrain, suggesting active exchange between surface and ocean. If the seafloor contains silicate rock, like Earth's, water-rock interactions, known as serpentinization, could produce hydrogen and reduce sulfates into sulfide. Exactly the compounds T. geothermicum chews on. Chemical parallel. On Earth, mid-ocean ridges yield hydrothermal fluids rich in hydrogen, hydrogen sulfide, methane, and metal sulfides. On Europa, tidal heating might generate lower temperature vents, around 10 to 30 degrees Celsius, but still rich enough to sustain chemosynthesis. Model projection. If Europa's heat flux is approximately 0.1 watts per square meter, compared to about 0.3 watts per square meter at Earth's ridges, vents would be smaller and fewer. But even a handful could create redox gradients spanning tens of kilometers. Hints of plume activity on Europa emerged from Hubble observations by Roth and colleagues in 2014, suggesting episodic jets of water vapor and ice. Clipper's MASPEX instrument, the mass spectrometer for planetary exploration, will fly through plume material, sampling trace gases at altitudes of 50 to 200 kilometers. If Thermococcus geothermicum-like life exists, we might detect elevated methane to hydrogen ratios. Laboratory simulations showed a signature ratio of approximately 1 to 4 methane to hydrogen under Europa conditions. Organic sulfur compounds such as dimethyl sulfide or thioesters that result from partial sulfide oxidation would be unambiguous biosignatures. Branching isoprenoid lipids, with unique mass peaks around 450 to 500 atomic mass units, are indicative of archaeal-type ether lipids stable under 800 to 1000 atmospheres and -1 degree Celsius. MASPEX's sensitivity down to parts per trillion for organics means even dilute plume ejector could yield signals. If detected repeatedly, these chemicals would point, albeit indirectly, toward chemosynthetic ecosystems under the ice. Even absent vents, Europa's intense surface radiation, approximately 540 rem per day, splits water molecules within the top few meters of ice, a process called radiolysis, Laboratory experiments, NASA funded in 2023, simulated Europa's ice, showing radiolytic hydrogen production rates of about 1 nanomole per cubic centimeter per hour. If hydrogen accumulates at the ice-ocean boundary, microbes could exploit it. Ice water microbes. They'd anchor to the underside of the ice, feeding on radiolytic hydrogen and oxygen, somewhat like Earth's subglacial Lake Whillans, where radiolysis supports small ecosystems. T. geothermicum analogy. Although optimized for vent chemistry, its sibling strains in the lab adapted to feed solely on hydrogen under -1 degree Celsius and 600 atmospheres, suggesting metabolic flexibility. This scenario expands potential habitats, not only hydrothermal vents, but also the ice-water interface, where radiolysis-generated hydrogen becomes a local energy source. Unknown vent distribution. Without seismic data, the exact number and location of vents remains speculative. Some models predict vanishingly few, risking patchy habitats. Ice thickness variability. While average ice thickness is 15 to 25 kilometers, chaotic terrain might feature local thinning, less than 10 kilometers, altering pressure and temperature profiles and potentially constricting habitable zones. Contamination risks. Earth microbes hitchhiking on future landers could confound detection, hence strict planetary protection protocols are mandatory. T. geothermicum broadens our view of habitability. Europa's lower heat flux means vents are cooler than Earth's, but life could adapt. The critical question: can these microbes reproduce under slow energy fluxes? Our lab data saying yes, but very slowly, is promising. Imagine tiny microbes in scuba masks, bobbing near an icy vent on Europa, holding mini hydrogen cocktails while dodging frozen plankton ghosts. They probably complain about weak currents compared to Earth's raging vents, but at least they get a view of Europa's lightning-etched cracks high above. By recreating extraterrestrial habitats in Earth labs, these microbes hint that life's resilience extends far beyond sunny shorelines. The revelation that T. geothermicum can persist at 1 degree Celsius and 800 atmospheres under Europa-like chemistry shifts our approach to searching for life. If Europa Clipper's MASPEX or SUDA instruments detect methane to hydrogen ratios around 1:4 or unique sulfur-bearing organics in plume material, it would validate the chemosynthetic hypothesis. Even if the plumes yield no biosignatures, we'll learn about non-biological geochemistry, refining models of Europa's ocean circulation and ice dynamics. On Earth, this discovery has inspired new deep-sea missions to explore previously inaccessible vents using autonomous submersibles equipped with improved high-pressure sampling. In astrobiology, it elevates Europa from a cold, inert sphere to a top-tier candidate for extant life, surpassing Mars's dusty plains for life detection priority. Funding agencies are already redirecting resources to support Europa-focused research, from lab-based hyperbaric studies to developing next-generation lander concepts capable of drilling through tens of meters of ice. Long-term Thermodesulfobacterium geothermicum inspires a broader redefinition of habitability. Scientists now consider that cold, high-pressure oceans with tidal or radiolytic energy sources needn't be rare. This paradigm extends to Enceladus, Titan, even exoplanets with subsurface oceans. The tiny microbe's legacy is clear: life finds a way in darkness and pressure, and in doing so, it expands our search for life across the cosmos. From Earth's darkest trenches to the ice-shrouded ocean of Europa, the tale of Thermodesulfobacterium geothermicum shows us that life doesn't just survive, it adapts and thrives in places we once thought impossible. Now it's your turn to dive deeper. Subscribe to Infinitia Verity for more mind-bending stories at the edge of science, myth, and possibility. Follow the Europa Clipper mission. It might just confirm the existence of alien life in your lifetime. Explore astrobiology. Read, share, and question the boundaries of life as we know it. Comment below. If there's life beneath Europa's ice, what do you think it looks like? At Infinitia Verity, we don't just ask what if, we dig into the what might be. Let's keep searching together.